Welcome to the new era of video creation with Bayozi. This is our new series on teaching deep learning. Today, we will discuss the Generative Adversarial Networks. Here are the contents. Generative Adversarial Networks, GANs, are a class of machine learning models introduced by Ian Goodfellow and his colleagues in 2014. GANs have fundamentally changed the way we think about generating data. They consist of two networks, the generator and the discriminator, that are trained simultaneously in a kind of game, where the generator attempts to create realistic data, and the discriminator tries to distinguish between real and fake data. Over time, the generator improves to produce more convincing samples, while the discriminator gets better at telling the difference. This setup creates a zero-sum game, where the generator tries to fool the discriminator, and the discriminator attempts to catch the fake data. The result is the generation of new synthetic data that can be indistinguishable from real data. GANs have become incredibly popular in fields such as image generation, video synthesis, and data augmentation due to their ability to create highly realistic outputs. GANs are built on the principle of adversarial training. The generator is a neural network that takes in random noise as input and generates fake data that mimics a real dataset. The generator's goal is to create data that is indistinguishable from real data. The discriminator, on the other hand, is a neural network that takes both real data and generated data as input and classifies whether the input is real or fake. The adversarial nature of GANs means that the generator and discriminator are trained together in a minimax game. The generator tries to minimize the discriminator's ability to tell real from fake, while the discriminator tries to maximize its ability to distinguish between the two. This back-and-forth training process pushes both networks toward improving their performance. The loss function in GANs is typically based on binary cross-entropy, where the generator tries to minimize the error in its outputs, and the discriminator attempts to correctly classify the data. The generator in a GAN is a neural network designed to create synthetic data, whether it's images, videos, or text, from random noise. The architecture of the generator can vary depending on the specific use case, but typically consists of layers like fully connected layers, convolutional layers, and batch normalization. The generator's task is to take a random vector, often from a Gaussian distribution, and transform it through a series of nonlinear transformations into an output that resembles real data. During training, the generator's goal is to produce data that is as realistic as possible so that the discriminator cannot distinguish it from real data. Essentially, the generator is trying to fool the discriminator into believing that the generated data is real. The quality of the generated data improves over time as the generator learns to adjust its parameters to generate more realistic outputs based on the feedback from the discriminator. The discriminator in a GAN plays a critical role in distinguishing real data from fake data. It is essentially a binary classifier that takes as input either real data from the training set or fake data generated by the generator and outputs a probability that the data is real. The discriminator is typically a neural network with a convolutional architecture in the case of image data, or a fully connected architecture for other types of data. During training, the discriminator's objective is to maximize its ability to correctly classify real and fake data. The discriminator is updated through backpropagation, based on the error between its predicted classification and the true label. The training of the discriminator is vital because the quality of its feedback helps the generator improve. It is a zero-sum game. As the generator improves, so must the discriminator, and vice versa. The adversarial relationship between the two forces both networks to learn effectively. Training GANs involves alternating between updating the generator and the discriminator. The discriminator is trained first to classify real data as real and fake data as fake. Then, the generator is trained to minimize its loss function, which involves creating data that can fool the discriminator. This alternating process is repeated many times. One challenge in training GANs is ensuring stable training. Both the generator and discriminator can become too strong relative to the other, leading to problems like the generator producing poor results or the discriminator becoming too effective. A common issue is the mode collapse, where the generator produces a limited variety of outputs. Stable training requires careful tuning of learning rates, the use of techniques like batch normalization, and balancing the training of both networks. The loss functions used in GANs, typically binary cross-entropy for both the generator and discriminator, are designed to optimize this adversarial training process. There are several variations of GANs that have been developed to address specific challenges or improve performance in certain tasks. The vanilla GAN is the basic form, consisting of the standard generator and discriminator networks. However, there are several enhanced versions, each designed for particular tasks. Conditional GANs, CGANs, add additional information, like labels or attributes, to both the generator and the discriminator, allowing for more controlled generation, such as generating images of a specific class. Deep convolutional GANs, DCGANs, use convolutional layers in both the generator and discriminator, making them especially effective at generating high-quality images. Cycle GANs, on the other hand, are used for image-to-image translation tasks, such as turning photos into artwork or changing the season in a landscape photo without needing paired training data. These variations have expanded the scope of GAN applications beyond simple image generation. GANs have revolutionized the image generation domain. One of the most straightforward applications is generating realistic images from random noise. For instance, GANs can generate entirely new faces that look like photographs, but are actually fabricated by the model. Another significant application is image-to-image translation, where GANs can transform an image from one domain into another. For example, turning a black and white photo into a colorized version, or converting a photo of a landscape into a painting. Super-resolution GANs can enhance the resolution of images, turning low-quality images into high-definition versions. Finally, style transfer allows GANs to transfer the artistic style of one image to the content of another, which has been widely used in creative industries and digital art generation. GANs have proven to be powerful in producing high-quality, photorealistic images across a wide range of applications. GANs are not limited to image generation. They also have applications in text and audio generation. One interesting application is text-to-image generation, where GANs are used to generate images from textual descriptions. For example, a GAN can take a description like a dog playing with a ball in a park and generate a realistic image based on that description. In speech synthesis, GANs are used to generate realistic human speech or enhance audio quality. They have also been used in music composition, where GANs generate original pieces of music in specific styles or genres. Text generation with GANs is still an emerging area, but there have been advances where GANs generate coherent and contextually accurate text, often for creative writing or chatbot applications. These applications demonstrate the versatility of GANs in areas beyond image generation. While GANs are powerful, training them comes with its own set of challenges. One significant issue is mode collapse, where the generator produces limited types of outputs, even when it is supposed to generate a diverse set of data. This happens when the generator learns to fool the discriminator by generating just a few types of outputs, which do not fully represent the data distribution. Another problem is the difficulty in balancing the training of the generator and the discriminator. If one network becomes too strong too quickly, it can overshadow the other, leading to training instability. Long training times are also common in GANs, requiring significant computational resources. Additionally, fine-tuning hyperparameters like the learning rate, batch size, and model architecture is crucial for maintaining stable training and high-quality outputs. Evaluating the performance of GANs can be tricky, as traditional metrics like accuracy and loss are not always applicable to generative tasks. One commonly used metric is the inception score, IS, which evaluates how well a GAN generates images by measuring the clarity and diversity of the outputs. Another widely used metric is the Fréchet inception distance, FID, which compares the distribution of generated images with that of real images. A lower FID score indicates better quality. The visual Turing test involves human evaluators assessing whether they can distinguish between real and generated images, providing a subjective measure of image quality. Additionally, precision and recall for generative models are used to evaluate how well the generated samples match the true data distribution. These metrics help researchers assess the quality and realism of the generated data. There have been several advanced GAN architectures designed to improve training stability and output quality. Wasserstein GANs, WGANs, address issues like mode collapse and instability by using a different loss function based on the Wasserstein distance, which improves the training dynamics. Progressive GANs use a novel approach to progressively train the generator and discriminator at increasing image resolutions, which allows them to produce high-quality, high-resolution images. The self-attention GAN, SAGAN, incorporates self-attention mechanisms to allow the model to focus on important areas of an image, improving the generation of complex images. BigGAN, developed by DeepMind, is designed for generating large-scale, high-resolution images with remarkable clarity and diversity. These architectures have pushed the boundaries of what is possible with GANs and enabled even more sophisticated applications. GANs have proven to be highly beneficial in healthcare applications. In medical image generation, GANs can generate synthetic medical images for use in training diagnostic models, especially when labeled data is scarce. For instance, GANs can generate realistic MRI scans or X-ray images to augment existing datasets, improving the performance of medical imaging systems. GANs are also being used in drug discovery, where they help generate molecular structures with desired properties, significantly speeding up the drug development process. Furthermore, GANs can be used to synthesize medical data, such as generating patient records for privacy-preserving research or generating data to simulate rare diseases. Finally, in personalized medicine, GANs are being explored for generating patient-specific treatment plans based on individual health data, leading to more tailored healthcare solutions. GANs have also made a significant impact on the creative industries. One of the most popular applications is in art generation, where GANs can create new artworks by learning from a dataset of existing art styles. This allows artists to collaborate with AI to generate new, unique pieces of digital art. In fashion design, GANs are used to predict trends and create new clothing designs based on historical data. The gaming industry uses GANs for procedural content generation, where game environments, characters, and assets are created automatically, reducing the need for manual design. In music and audio generation, GANs are used to compose new music or enhance existing pieces, offering a fresh way of exploring sound and musical composition. These applications demonstrate the growing influence of GANs in creative and entertainment fields. With great power comes great responsibility. GANs present several ethical considerations and risks, particularly in the realm of deepfakes and misinformation. GANs can generate hyper-realistic images and videos, making it easier to create misleading or harmful content, like fake news or impersonation videos. This raises concerns about privacy and the use of synthetic data in ways that could violate individuals' rights. Additionally, the ability of GANs to generate artwork raises questions about the future of creativity and the value of human-made art. As GAN technology advances, it is crucial to implement regulations and responsible use practices to ensure it benefits society while minimizing potential harm. Researchers, artists, and policymakers must work together to navigate these challenges thoughtfully. In conclusion, GANs have proven to be a transformative technology with a wide range of applications, from image generation and text-to-image translation to drug discovery and creativity in art. As GANs continue to evolve, ongoing advancements in architecture, training techniques, and evaluation metrics will help overcome existing challenges like mode collapse and training instability. The future of GANs looks promising, with new developments likely to push the boundaries of what these models can do, including generating even more realistic data across diverse domains. However, there are still significant challenges ahead, such as improving model efficiency and addressing ethical concerns. As GANs become an integral part of next-generation AI systems, it is important to continue advancing the research and applications of GANs while considering the societal implications of this powerful technology.